Good morning, ladies and gentlemen. It's always a great pleasure. This is the second time you've been kind enough to invite me to give the talk at the beginning of your amazing conference. It's a very nostalgic occasion. I was calculating it's exactly 38 years since I showed up on this campus as a new undergraduate in electrical engineering. Not quite in this building, because it's changed a bit, I'm pleased to say, in the 38 years since then, and then graduated 3 years later. So there we go, that's my 35th anniversary. What I'm going to try to do today is get about 2 hours worth of material into 20 minutes, so that you have 5 minutes to ask questions. It's that kind of concentration which I'm hoping to achieve. Most of what I'm going to say is contained in this book, which obviously I would recommend, but it may even be on your reading list, who knows, because it's work from the UK Energy Research Centre, and I'm sure you will know that the HQ of UKirk is located on the Imperial campus. The director is Jim Watson, who is a professor here and at Sussex. So these are the 6 topics I want to cover. They cover, obviously, some of the engineering stuff that I learned so long ago, and most of which I've probably forgotten. They also then go on into economics, because that was actually the discipline in which I got my PhD, and then into policy analysis, which is what I mainly do now, and you'll have noticed that that's the title of my chair. Don't need to spend a lot of time on this. I'm sure you will have done that. In your course, inexorable increase in energy use and CO2 emissions. So there's a country breakdown there, and you can see that going all the way back to 71, we've had growth in both those variables, which shows the extent to which the energy system is still very much linked to fossil fuel use. Energy is very unequally consumed, and in a global kind of course such as I know this is, you will be very interested in that. You've got your high-consuming countries, you've got your major developed economies, emerging economies, and lower-income countries, all with very, very different per capita emissions. And that's one of the major elements that feeds in, obviously, to the climate negotiations. Both that element and the fact that their cumulative emissions over historical time has also been very different. And as carbon dioxide is a stock gas, that means that it's very easy to identify those countries that have been most responsible for filling up the atmosphere with carbon dioxide and precipitating global climate change. So here are the top 10 emitters, and you can see that the big emitters are China, United States. That looks very different now to what it did in 2000 as a function of China's colossal economic growth since then. But again, you get a very different picture if you look at per capita emissions. And China down there, very interestingly, China kind of more or less now at the per capita level of the European Union. So it's not anymore the case that China is a very low per capita emitter. But obviously there are developing countries that emit much, much less. You've got India on there, and clearly sub-Saharan Africa is much lower still. That's what the emissions have to do if we are to have any chance at all of staying within 2 degrees, let alone 1.5 degrees, which is what the politicians said their aspiration was last December. And and I'm sure you, I noticed there's a huge amount of work going on in bioenergy on this course from the posters, are thinking about, from your own perspectives, how on earth that very, very different trajectory might come about. And obviously the policy implications of that are very much something that I'm engaged in. So, it's only relatively recently I spent most of my time thinking about the low carbon energy sources because of that trajectory, but actually, as we've already seen, the energy system reality globally is that it's still dominated by fossil fuels, and that shows the extent to which that is still the case. The 3 big bars at the bottom, the big swathes of energy use, coal, oil, and natural gas, a little bit of nuclear, biofuels and waste, and other renewables up at the top. They're growing, certainly, but they're still a small proportion of global primary energy demand. Possible to distinguish between countries, so we've got OECD countries on the left, non-OECD countries on the right, and you can see that the OECD countries' energy use has more or less plateaued. It's plateaued at a high per capita level, as you will have noticed from the second or third slide that I showed, but of course developing country use is increasing, and since the 1990s is increasing at an accelerating rate as a response to some success in economic development. So although in carbon terms that's unlikely to be positive, in economic development terms, in terms of the Millennium Development Goals, that is a good thing because per capita incomes in many parts of the developing world have increased dramatically. There is an enormous quantity of hydrocarbons out there. I'm of the generation that grappled with the limits to growth arguments in the 1970s, and all sorts of very wrong predictions were made at that time about possible shortages of hydrocarbons. And I actually did my PhD on the relationship between economic growth and environmental sustainability, and I hope I'll have a bit of time to get into some of that before the end. But those are supply curves of oil, gas, coal. Those three, the three here. Oh, whoops. That's these three. And you can see that the costs of extraction vary very greatly. You can see that there are lots and lots of different kinds of oil and gas, rather fewer kinds of coal. And this little diagram here illustrates the extent of the climate change challenge. So the dark brown is reserves, the light brown is resources, and we need to distinguish pretty rigorously between reserves and resources. And the little green bar is what the IPCC calculates we can afford to emit into the atmosphere if we want to stay within the 2-degree temperature rise limit. The light green is the level of uncertainty associated with their carbon budget. But if you look at the carbon that would be emitted if we burnt all the oil, gas, coal and lignite reserves, not resources, that comes to about a factor of 3 more than the carbon budget. If we burnt all the resources, that would come to a factor of 10 more than the carbon budget. So you can see that the problem is not that we're going to run out of these jolly hydrocarbons. The problem is that we can't afford to burn them and release them into the atmosphere. There's far more to do. Those curves are the work of someone who is now unfortunately no longer at UCL. He's working for the International Energy Agency. Those of you who are academics will know the extraordinary pleasure and privilege it is to have a genius as a PhD student. And this guy is a genius. So his name's Christophe McGlade, and we published a paper together in Nature, which was entirely his work, at the beginning of last year, and it's had more media citations than any other paper on climate change in 2015. So that was pleasing. It used our energy system model, TM-UCL, which Christophe was very largely responsible for building. You've got a times model at Imperial now, so many of you may be familiar with working with that. It's an energy system, goes from energy service demands at this end through all the fuels that you need to satisfy energy service demands until you come to primary energy here, and then it has a climate module so that we can restrict the carbon emissions to achieve certain temperature increases, and that was the work that we did. I'm not going to spend any more time on that. You can ask me some questions about it if you want to. This is the paper that we published in Nature, and its novelty was twofold. People had already calculated that there was about 3 times as much carbon in the fossil fuel reserves as we could afford to burn within the budget. What we did was to divide that between coal, oil and gas on the basis of those supply curves and identify in which geographical regions these resources were located on the basis of the 16 regional breakdown that we have in the model. It's a cost optimizing model, so like a good rational economist, it burns the cheapest fuels first, and then the more expensive fuels are just left unburnt. Now, we know the world doesn't work like that, but nevertheless, that's an interesting kind of thought experiment. If the world did work like that, where would the unburnt carbon be? And here was the answer, which people get pretty interested in. So you can see that there's a lot of coal unburnt. This is not surprising, given that coal is easily the most carbon intensive of the fossil fuels, but a substantial proportion of oil and gas remains unburnt, and you can see very large absolute quantities. So if we look at the Middle East, and of course this is mainly Saudi Arabia, but also the other Middle Eastern countries, that's 263 gigabarrels of reserves in Saudi Arabia that would remain unburnt. So I leave you with that intriguing thought and move on. Very interesting to see which fossil fuels get burnt, the kind of trajectory over to 2050, which was our time horizon. This is the 5-degree scenario, which is more or less no climate policy, and then this is the 2-degree scenario, which was the one that we were most interested in. And you can see, interestingly, that more gas gets burnt in these middle years of the projection period than in the baseline. Why? Well, clearly because gas here is substituting for coal, which falls off a cliff. And that part of the discourse about gas being a transition fuel is now well in the rhetoric. We are very cautious about that because it depends on the region. Some regions have enormous scope for coal gas substitution. China, India, United States going on as we speak, and some other countries. But a country like the UK has already had its coal gas transition. We had most of it in the 1990s, so that there's relatively little coal left, and what there is due to be phased out anyway by 2025. So there isn't a lot of scope in the UK for that. We'll sometimes hear the government, which is very keen on fracking, trying to justify that policy on the grounds that we can substitute for coal. We think, and UKIRK thinks, because we've published a briefing on this subject, that that's a very risky endeavour if we want to meet our climate change commitments under the Climate Change Act. So just some intriguing stuff there. I haven't got time to go through this in any detail. You can see there's a lot of electricity in the 2-degree scenario. We've got 2 degrees without with no bio-CCS. We've got 3 degrees and 4 degrees. You can see there's a lot of electrification in the low carbon scenarios as it takes over some of the heavy lifting on heat and transport. You can see that here the carbon intensity of that power generation goes negative towards the middle of the projection period. As bio-CCS comes in, if you can't do bio-CCS, then the model has to work a lot harder, and you can see that the carbon price here without bio-CCS is much, much higher in order to incentivize those carbon reductions. And you can see that, thinking back to the per capita emissions that we started with, you can see that there's very much convergence between these per capita emissions, with the high consuming countries coming down and the low and middle income countries not increasing to anything like the extent that they might have done. Okay, so that's that. I've got 5 more minutes for these last 3 sections, so I'm going to go even faster, and you can come back to me and ask questions if you feel so inclined. You will all know, of course, the framework within which global climate policy is now conducted. It is conducted at all levels, but I'm not going to talk at all about the city and local levels, just very briefly about the global and national levels. The Paris Agreement, I'll be very happy for you to have these slides if you feel that I've gone too quickly and you want to revisit them and have a look at some of these issues. The Paris Agreement was a quite extraordinary achievement in the sense that it might have achieved nothing at all, and actually what it did achieve, bringing all countries into a unified framework, making commitments which were their commitments and which therefore they had some commitment to. We know it's not enough for the 2 degrees scenario, and will be very interesting to see in 2018 when these commitments are revisited, whether countries will in fact tighten them up in order to get closer to that 2 degrees. But a very, very interesting agreement. Some analysis there as to why Paris in 2015 was successful, whereas Copenhagen in 2009 was not. I haven't got time to go into it, all those bullet points, but again, we can explore that later if you want to. I'm sure you've heard of the energy trilemma, whereby practically all countries now are seeking to achieve 3 objectives with their energy policy. They're seeking to achieve affordability. That's nothing new. Countries have always wanted cheap energy. They're seeking to achieve energy security. That also is nothing new. Countries have always wanted to have security in their energy system, and that's a complicated concept. Now, of course, they're seeking to achieve decarbonisation as well. That one is new, and certainly is new for developing countries, which up until now really have not have thought that this is something that developed countries need to do, but within the Paris framework now, everyone is expected to do something. So that's where we are there, and this is a very enthusiastic clicker here. So on it goes. And this is all made more difficult in terms of the decarbonisation agenda by the fact that we also have the sustainable development goal of ensuring that all people everywhere have access to modern energy sources, so that we get rid of traditional biomass, which has enormous health impacts, and people have access to modern fuels, including, of course, electricity. Some 1.2 billion people don't have reliable access to electricity yet, and so how that electrification is going to take place is clearly enormously important. These are the 3 elements of energy policy which are normally cited as being important, and I spend a lot of my time thinking about the balance between them. I think the only thing I would stress about them is that you need all of them. There are some economists, of whom I am not one, who believe that markets work so well that all you need is carbon pricing. And you can hear that and you can read that in economics textbooks. I think that's bunk. And I think I've always been an advocate of carbon pricing, but I think if you can support carbon pricing with appropriate regulation for those parts of the market that are not particularly responsive to prices, and if you can support it with R&D support and technology deployment support, then you get much more bang for the buck out of any carbon prices that you've managed to implement. And I'm pleased to say that was Lord Stern's view in the Stern Review, and everything I've seen since then has suggested that that is the approach that's most likely to yield fruit. This is an adapted picture from Michael Grubb's excellent book called Planetary Economics. Managed to persuade Michael to come and join us at UCL a couple of years ago. And again, it's a complicated picture. I haven't got time to go through it, but it provides a pretty rigorous theoretical framework for suggesting that where markets and prices work, we should use them with carbon pricing, but where they don't, we need standards and engagement, strategic investment, particularly in order to encourage innovation. This is an analysis by the New Climate Economy people as to where these carbon emissions reductions might come from. Clearly, they won't happen by themselves. You will need policy measures to produce them. But this very large carbon reduction, in order to get to a trajectory for 2 degrees, this is the 2030 picture, is perfectly possible. It's very challenging, but the analysis shows, if you look at it sector by sector, that you can do it. Which leads on to the co-benefits. Were we to do it, we would not only get carbon out of the system, but we would get enormous health co-benefits. This is a picture from the UCL Lancet Commission report that was published in the Lancet last year, which really tried to bottom that out, what would be the health co-benefits of decarbonisation, and they are colossal, and they are normally left out of account when countries do their analysis as to what their benefits of decarbonisation are. And the reason that they're normally left out of account is that they are externalities at the moment. They don't feature in the price of burning fossil fuels which consumers pay. And this is a diagram that comes from the IMF paper that was published again last year. Lots of papers leading up to the Paris conference, of course. And you can see that these dark bars at the bottom here are the actual financial subsidies that countries pay to fossil fuels. I mean, they're not small, they're about £500 million, which is considerably more subsidy than we currently give to renewables globally. So there are large financial subsidies still for fossil fuels out there, more than for renewables. But these much bigger bars are the externality costs of global warming, and here we have the local air pollutants, which so disfigure the cities, not just in the developing world, although obviously that's where it's worse, but also in cities like London. And you will be aware that there are several thousand excess deaths in London every year because of our failure to control local air pollutants from the combustion, mainly of fossil fuels. Okay, I noticed Maria looking nervous over there, so I'm not going to spend any time on this last section at all, which is a shame, because for me as an economist it's just about the most interesting, except to say that there's been an enormous shift in perceptions of this decarbonisation agenda from an economics point of view. But 10 years ago, the Stern Review was writing that the costs of decarbonisation were going to be 1 to 4% of GDP, and it was still a good investment because the cost of not doing it would be much higher, but that was further down the line. Now, work from the New Climate Economy and others is suggesting that actually the innovation benefits of moving in a low carbon direction mean that we're going to get short-term economic benefits. And when you add to that the co-benefits of reducing air pollution, then it's something which is a kind of no-brainer now in the short term for the present generation. And one of the big political difficulties, of course, with climate change has always been that we're living now, we want to have a good time now, we want to do all the things that burn fossil fuels now, and future generations, well, they've never been terribly influential, they don't vote, they can't speak, and so we tend not to give them very much weight in our political decisions. So that change in the discourse, that actually, economically, there are benefits now from decarbonisation, is enormously important. And in my view, that was one of the reasons why the Paris Agreement came about, whereas the Copenhagen Agreement only 6 years before. And one of the reasons for that cost reduction is the work that people like you do on these technologies. That these low-carbon technologies have come down in cost absolutely phenomenally, much faster than non-technologists that, like me, believed would be possible. So thank you, China. Thank you, Germany, for the commitment to the support, particularly those two countries, but there are others, obviously, as well. UK's done a little bit. Because that has really changed the discourse and the prognosis for it. So you need to do a lot more. You need to get these costs down even further, because the only way we'll really make the decarbonisation happen at the required speed is when these low-carbon technologies are cheaper in financial terms than the high-carbon technologies that they need to replace. I've gone a little bit over time, but only a little, Maria, so I hope we will have time for a few questions.
Many thanks to Professor Ekins for his speech. Now I would like to invite questions from the audience. Artemis, Phoebe has one.
What do you think of so the INDCs from Paris are non-binding? Should they be binding? And like, if so, how could they be made so? Do you have any view on that?
Well, firstly, they couldn't have been binding, because no one would have committed to them if they had been. So that was quite clear. So we got the best that was politically feasible. I think there's quite a lot of peer pressure. And what I hope is that as we move into 2018, countries will actually start looking at the countries they regard as their peers, those on a similar income level, those at a similar per capita emission level, and will start to try to outbid each other in order to appear good in these international contexts. And I hope that we will move to a situation where they do acquire the status of international law. It was always, everyone said that the Kyoto Protocol was legally binding, but actually it wasn't. When Canada realised it wasn't going to meet its Kyoto Protocol targets, it simply said, sorry guys, we're withdrawing from the Kyoto Protocol. There were no sanctions. It did get a bit of bad reputation, so people like me, you know, were pretty angry and we dissed Canada a bit, and you know, I don't suppose Canada cared. They were making shed loads of cash out of their oil sands, and that was the reason they couldn't come anywhere near their Kyoto target. So money spoke. So we were never going to get a legally binding. It's not entirely clear what legally binding would have meant in that context, but I hope that countries will take these commitments seriously.
I'd have a question in regard to the energy use that goes into the primary production of resources, like particularly mining and metals and minerals, where I was wondering what your view was on the impact of technology changes on the savings essentially of energy from the material side, material efficiency side, because we're focusing on technology a lot on the energy production, but there is also that impact on the materials side,
course,
from
yeah.
primary versus secondary production, from
No,
recycling.
that's a really important question. Metals currently consume about 8% of global energy, so the mining of metals, and that's a lot. And obviously, many of the low-carbon technologies require quite a bit of metal, especially wind, for example. So that's a big question. And the question is then, well, firstly, what are the carbon emissions of producing that metal? And secondly, is there enough metal of the different kinds? And you will have seen these pictures of the periodic table that show that actually these new technologies use an enormous range of the metals from the periodic table. I think that, the last thing I'll say about that is that the UNEP's International Resource Panel, which I'm a member of, I was the lead author of a report on resource efficiency where we published a summary for policymakers earlier this year. And we specifically did some modelling there to show what the relationship between resource efficiency policy was, which is exactly what you're talking about, or you know, if we make more efficient use of the primary inputs, compared to explicitly climate policy. And it's absolutely clear that if you have resource efficiency policy as well, then A, you can reduce your emissions much more. So it went from, I think, if I just remember the number, something like 64% reduction from a certain year down to 73%, which is a big chunk of what's left. But B, the economic outcome is better because resource efficiency is economically beneficial as well as being beneficial in carbon. A lot more research to be done on that, so I would encourage the next generation of MSc students on this course to think about actually looking at the metals and materials implications of the low carbon transition, because that's a relatively recent research topic.
Okay, many thanks. We have to close the Q&A now because there's an ambitious number of presentations going on today. Again, thank you, Professor Ekins.
You're very welcome.